Okay, so these notes for the first part of Unit 5, we're going to go over the periodic table and basically how we divvy it up into groups. And so this one shouldn't take very long. So we're going to go ahead and get started. So first slide here, you can just kind of see how our periodic table is divided all into groups. So not everything is the same. You have some things that are metals, you have non-metals, you have solids, you have gases. You have some of these that are even liquid at room temperature. Okay, so we're going to talk a little bit about how the periodic table was, how it came to be what it is today, and then basically how we divide it into groups and things like that. Okay, so our first slide we're talking about is from Dmitri Mendeleev. So he was the first to develop a useful periodic table. Okay, so we had a lot of people working with elements around that time, but he was the first one to kind of arrange elements by atomic weight. Okay, so the big key thing here, that's why I have it underlined and bolded, is that he was the first one to develop a useful periodic table, but he arranged it by atomic weight, so just simply by mass. Okay, and since he was a smart individual, he knew that there were probably things that he didn't discover yet, and so he left gaps in the periodic table for future discoveries. Okay, then we moved on to a little bit later, we had Henry Mosley. So Henry Mosley, he was the first to arrange it by atomic number. Okay, so that's his big key contribution right there. Is because why he did that is because when you arrange them by atomic number, you can put them into groups that have similar characteristics. So you can have like noble gases, that would be your far right column over here on your periodic table. So they all have the same kind of characteristics. So that's the way, and he also left gaps for future discoveries as well. Okay, now we're talking about organizing the organization of a periodic table. Okay, we have groups and periods. Okay, so groups are going to be your vertical columns on the periodic table. So they're the ones that go up and down. Okay, so like when you see at the top of your periodic table where it says group 1/1A, and your next group is going to be up and down, it's going to be 2/2A. That's what a group means. Okay, and the reason why they have the same characteristics is because they have the same valence electrons. So remember, valence was our outermost electrons. Okay, and the perfect number of valence electrons is 8. Okay, that's called the octet rule. Okay, so valence electrons, again, are your outermost electrons versus core electrons are everything towards the inside. Okay, so if you look at the top of your groups, you have 1A, 2A, then you're going to have 3A. You're going to jump across that transition section, that big D section, and it starts again at 3A, and then 4A, and then 5A, 6A, 7A, and 8A. So those are your valence electrons. Okay, the max number you can have is 8. Okay, then you have your periods. So periods are the horizontal rows. Okay, so they're the things that are going side to side. So when you look over to the left side of your periodic table, where you start seeing things like 1, 2, 3 going down the side, that would be your period. Okay, now just because they're in a period does not mean they have common characteristics. Okay, that's just how they line up, is just horizontal. Okay, so again, groups, the vertical columns are the ones that share common characteristics. That's why they're called groups. Okay, so now we're going to move on. So the main groups on the periodic table, you have metals, nonmetals, and metalloids. Okay, and I'm going to use a periodic table here in just a second to illustrate this. Your metals are going to be on the left side of your staircase except for hydrogen. Okay, and I'll explain that here in a second. And nonmetals are going to be on the right side of your staircase, and then metalloids are going to be on the staircase except for aluminum. Okay, metalloid just means they kind of act like both. They can act like a metal and a non-metal. They're just kind of stuck in that kind of middle ground. Okay, so I'm going to come down here for a second and pull up the periodic table that you should probably have. So this is the one that you have in your class. Okay, so again, remember that 1A, 2A, 3A. So this is what I'm talking about right here. So 1A, 2A, jump across your D section. You have 3A, 4A, 5A, 6A, 7A, 8A. So that's how you can tell how many valence electrons you have. Okay, so remember in this last unit we did Lewis dot structure. So if I looked at oxygen, oxygen has 6 valence electrons. So that's why we drew 1, 2, 3, 4, 5, 6 dots. So that means it has 6 electrons on its outer core that it can use to share with another element instead to create compounds. Now your whole middle section, which we'll talk about here in a second, basically starting right here at your D section and going all the way to the staircase, that's called your transition metals. So their charges or their valence electrons can vary depending on who they bond with. So that's why they do not have a definite valence electron. And again, we'll talk about that a lot more in this unit. So what we're going to do now is we're going to talk about those metals, nonmetals, and metalloids. Okay, so let me clear some room. Okay, so your metals are going to be everything to the left of this staircase right here. So basically everything besides the ones that are touching the staircase to the left is going to be considered a metal. Okay, now to the right side of the staircase, that is going to be considered a non-metal, which makes sense. If you look at helium, oxygen, fluorine, nitrogen, those would not be metals. Okay, then you have metalloids. Besides aluminum, metalloids are going to be boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Okay, so those are the ones that are going to act like metals and nonmetals. They're going to kind of share characteristics of both sides, so that's why they're kind of stuck in that middle ground. Okay, so again, your metals are to the left of the staircase, your nonmetals are to the right of the staircase, and then your metalloids are going to be along that line. Okay, so now let's come back up here. Okay, so that's what we just talked about right there. And then we're going to talk about group 1A. So that's your first column on the far left of the periodic table. Those are called your alkali metals. Okay, so group 1/1A. Okay, so 1A means they have one valence electron, so that's how I got that right there. Okay, and they are very reactive. So reactive means that they want to bond with somebody else. Okay, so that means they can bond with a lot of people, and so that makes them very reactive. However, that can make them violently reactive if they're reacting with water. Okay, so they're explosively reactive with water. And they're never found alone in nature. Okay, so again, very reactive means they need to basically bond with somebody. So that's why it's very hard to find them alone and not bonded to something else. Okay, and reactivity increases as you go down. So that means as you go down the group, okay, group 1A, they're going to become more reactive. Okay, now these are metals, as you can see from the pictures. They typically look like metals, what you would think a metal would look like. And they're very soft and easily cut, so very soft metal. Okay, then you have your alkaline earth metals. That is your group 2A. So they have 2 valence electrons. And you will see these valence electrons are a very big deal in this unit. Okay, so make sure we pay attention to that. Okay, they're a little bit less reactive, but still not found alone. So meaning they don't need to bond as much, but they're still pretty reactive, but they're still usually not found alone. And they're going to be a little bit more shiny and slightly harder. Okay. Then you have your less interesting groups. There's really not a whole lot going on in these. Okay, so we're just going over the names of them. You have your boron group. Okay, then you have, which is 13/3A, which has 3 valence electrons, and it's made up of metals and metalloids. Then you have your carbon group, which is 14/4A, which is 4 valence electrons, and it's made up of metals, nonmetals, and metalloids. Then your nitrogen group, 15/5A, 5 valence electrons, metals, nonmetals, and metalloids. And oxygen group 16/6A, which has 6 valence electrons and nonmetals and metalloids. Okay, so again, those aren't very much of a big deal. I'm just explaining how there are different groups. Okay, then we're going to move on to our halogens. Now, halogens are going to be a little bit more interesting than the last one. So halogens is that second to last group on the periodic table. Okay, starting with fluorine and going down. So that's in that group 7A, so which it has 7 valence electrons. Okay, so remember the perfect number of valence electrons is 8. That is your octet rule. Okay, so that means they have 7 valence electrons, meaning they only need 1 more. Okay, so that means they are very reactive, meaning they want to bond with somebody to make that 8. Okay, because that 8 basically makes them whole. Okay, so think of it as like something that you're missing. Okay, and that you need that one thing to make you whole, so that's why they're going to be very reactive with other people. With other elements. Okay, so it needs 1 more electron to make that octet. Now these are also found in diatomic pairs, so that means they're not found by themselves. So diatomic means instead of fluorine being by itself, it's just going to pair up with itself with another fluorine, so it's going to be F2. Okay, chlorine's not going to be by itself, so it would be Cl2. Okay, and we'll talk about those here in just a second. And they're found in many of your common salts. Okay, so what you would think of as salt, that's where they're usually located. Then you have your noble gases. So noble gases is that last group. So hopefully this is kind of a refresher because we use noble gas shortcut when we are doing electron configuration and orbital notation in the last unit. So noble gases are going to be that very last column on the very far right of your periodic table. So it's group 8A/18. Now they have 8 valence electrons, meaning that perfect number was 8 is achieved. So that means they do not react. They don't need anything. So if you're whole, if you have everything, I don't need anything else. So they're not going to react with anything. They're just going to do their own thing. and then they're all gases. Okay, so that means that they're colorless and odorless. Okay, so the reason why we have colors here is because when you add a current, like a specific current to a gas, we can change colors with it based on the element. Okay, then we're going to talk about our transition metals. So transition metals, we kind of talked about a little bit down here in the periodic table. Your transition metals start here at group 3B, and they're going to go all the way to that staircase, basically. Okay, so again, transition metals mean that they do not have a certain valence electron. Okay, they will vary, and we will use that a lot here in a little bit. Okay, and they do not follow common patterns, so they're different, so you can't really group them together. Okay, they're going to be a wide variety of different elements there. And this includes the lanthanides and actinides, which are down here in the periodic table. Your lanthanide series is going to be this 4F column. Okay, and basically these are just going to act like lanthanum. Okay, so that's why they're kind of along that same row as lanthanum. And then your actinide series is going to be this bottom column, this 5F column. Okay, and they're basically going to act like actinium. Okay, so not a whole lot there. We're not going to spend a whole lot of time in the lanthanide and actinide series, okay, but it's just something to know. Okay, then we're going to move on to our diatomic molecules. So remember diatomic, so di means two. Okay, these are the elements that have to be in pairs. They're the ones that cannot be alone. They don't want to be alone, so they're going to form covalent bonds, which we're going to talk about here in a second. Covalent bonds with each other if they do not have another element to pair up with. So if they have another element to pair up with, okay, they don't have to be by themselves. Okay, so if they have someone to pair up with, they don't have to be Br2, I2, O2. Like look at something like this, like H2O. Okay, so there are two hydrogens to mix up with this oxygen, but you can see here that there are not two oxygens, and oxygen is one of my 7 diatomic molecules. Okay, so they do not have to have two all the time if they have someone to pair up with. Now, if they're alone, okay, there are these 7 elements that have to be in pairs. The way I remember this is the name Brinkelhoff. Okay, whatever you need to do to help you memorize things, that's fine. That's just something I've been using over the years, is Brinkelhoff. So that is Brinklhof. Those are your 7 elements. You have bromine, which is Br. Okay, then you have iodine, then nitrogen, chlorine, hydrogen, oxygen, and fluorine. Okay, so if you ever see something like this, if you see bromine by itself in a formula, which we're going to be seeing here in a little bit, that would be incorrect because it cannot be by itself. It has to be Br2. If I saw something like chlorine by itself, that would be incorrect. It has to be Cl2. So those are your 7 that you will need to know that have to be in diatomic pairs if they're found alone. So again, Brinkelhoff should help you out. Memorize that. That helps me quite a bit. So if you want to find something different, that's totally okay. Okay, so hopefully that kind of explained the periodic table a little bit. We're going to be using these valence electrons and charges a lot more in the upcoming videos. So hopefully this helped a little bit.